Good morning, Jean-François from Chrysalide Engineering and LC. It's a shop for electronic devices. I'd like to talk about CNC machines, 3D printers, and on this video the design of a stepper board I designed for these machines. Here's a RISC-V two-way stepper driver motor board I designed with KiCad and intend to use for various projects of CNC and 3D printers. On schematics we start from the supply voltage, protection fuse, protection diode, the buck converter, 7.4 rail, and then we have the LDO to make 3.3 volts for the microcontroller and stepper driver logic. We have microcontroller, two drivers, the oscillator for the microcontroller, and the oscillator for the stepper driver clock. And from there we go directly to the motors. We have the test points for various rails, current for two driver motors. And we have external provision for external control for the steps and direction for each of the two motors, plus the enable pin, and UART control and program pin for the microcontroller, as well as external enable, which goes to the drivers, motor drivers directly. That's very simple, and we see that the microcontroller can control the driver mode, decay mode and current reference, so that we can set up current by microcontroller, change and adjust according to the need, or even use as a test bench. We have 0.3 ohm for the current measurement on the motor phase, and the RC filter for the current reference coming from the microcontroller. The output to the motor is up to plus 24 volts and 2.2 amps, about 2 amps. This board is connected to an external computer or a hardware control board, so that we have the serial pin control for the motor's direction and steps, or to send higher level commands such as position the motor to a certain X and Y, and then the firmware can handle the controls. So I intend to make also the firmware on this board. There is actually a prototype firmware for a similar board, and I use directly the timers on the microcontroller to make accurate movements, because one thing I found out on these stepper motors, they are very sensitive to accurate timing. The issue they have is that if there is timing inconsistency, the motor may lose steps, because for the motor it's like a sudden change of speed. So that's why I decided to use a timer with interrupt on the firmware on this microcontroller. And also the current reference and decay mode can be tweaked, so that maybe various motors or various machines need different modes, control mode. On the board layout we have programmation port and UART control port, J5 over here, step and direction pins for each motor down here, test points for power supply, current reference and measured current through the shunt, and the terminals for the driver for power supply, fuse and protection diode. And also to be noticed, I use ground plane on each side. I used to have a ground plane on the top and power supply plane on the bottom. The reason for that is often we need ground for some components with maybe surface mount, and therefore the ground plane goes on the top layer. This is the board, 90 by 45 mm. Here is the buck from, I don't know, this company changed the name, I believe. It's a AOZ 1282, it works at 450 kHz. It's a SOT23, and I don't use the enable pin, and we set up to 7.4 volt output. Nothing very special in this chip. It goes 4.5 to 36 volts, and we'll use it up to 24 volts. Next we go to the linear regulator, because we want to get rid of the 200 mV oscillation. So for that purpose we use the microchip 1703. Again, SOT23 package, and we make 3.2 volts. Nothing complicated to use this chip. We just have the bypass capacitors, and we use up to plus 18 volts. So for application 7.4 volts. They define short circuit as 400 and nominal as, I believe, 250 milliamps. On the microcontroller side we keep the 24 microcrystal, and we use all of the pins for serial communication, external GPIO control, and the driver motor controls. The only thing we cannot do is use the power save mode and enable on the microcontroller. Therefore these are wired to the external pin, so that we can cancel the power to the motors from external. This board very simple but versatile, and we can embed in this microcontroller G-code interpreter, which I'll try to implement for this board to make an application that's interpreting the code on the microcontroller. I thank you. That's for the moment. I need to build this board, and I will show the software when these are being polished.